Welcome back to ECE 441A, 541A. The next time you will be in this classroom is for exam number 3. That's in a week. You won't be physically here until then, and well, hopefully you're physically here now, but you may not have physical presence, but you definitely have activities and deadlines that you have to meet in between now and then. One is homework number 6 is due today, and homework number 7 is due Wednesday, and obviously then the exam is a week from today. And they're the reasons behind not having class the other 2 days of next week. But I will be available for office hours if you want to ask questions in person next Tuesday from 8:30 to 10:30. Lab number 3, I hope it's clear that it's not due until the last day of class, which isn't that far away, but the material, the concepts, the techniques that you have to apply in lab number 3 will be a part of exam number 3, and that you will have to be able to perform in a week. And here are the dates and the deliverables associated with the project for those students in 541. Here's a listing of the material, lecture topics in unit number 7, and all of those have not been in person. Maybe, I don't know how close you're paying attention, but we've now done 1, controller overview, and 2, a phase lead controller design. Between when we did phase lead and today, I've now supplied you with a phase lag controller material, video on D2L that discusses mainly a PI controller, which allows you to think about steady state accuracy. The phase lead was worried about transient behavior. Today we will actually get into lecture 7.4, which is controller design evolution. How do we work our way from a pure gain controller to a phase lead controller to a PI or PID controller? And that's really what you're doing in lab number 3. And we'll talk through that today in today's controller design evolution material. If we have time, we will talk about stabilizing unstable systems. That will be on the exam, and there is actually a video already posted for that particular topic, stabilizing unstable systems. And in particular, you might see that even if you start with an unstable system, you might have to actually introduce a controller that has an unstable pole or something that you wouldn't maybe intuitively think about in order to actually stabilize the closed loop system. And that's covered in video 7.5. Today what I want to do is lay down here. We want to go through this progression or evolution of different controller designs, and that then says we'll start with a pure gain controller, then we will look at a phase lead controller, and then we'll do a PID controller. That was bothering me. I didn't realize we didn't have a screen down, and you were probably wondering, how can I read all of this material from the wall? But now you can read it very cleanly, hopefully, although that screen looks a little bit. Need to pull the iron out and stabilize that screen a little bit. I'm actually surprised I knew which screen was which, but I pushed the right button. Where were we? Oh, so you're going, where in the world? I can't connect all of these things to reality. And here I'm trying to take us all the way back to homework assignment number 1, I think, where you had to derive the transfer function for this op-amp circuit. Well, this op-amp circuit is actually a phase lead, phase lag controller. That's all you need to build some of these controllers, is an op-amp and a couple of capacitors and a couple of resistors. In this particular circuit, the input is V sub I, and that might be where you inject the air signal. Then V sub 2 is the output of this controller. This controller is doing some kind of filtering, and what it does depends obviously on these parameter values, R1, C1, R2, and C2. And unfortunately in the book I think the subscripts on the C's are missing, but I've put in some subscripts here to make it a little easier to keep track of which one's C1 and which one's C2. But this you can derive the transfer function for by simply doing KCL at the inverting junction of this op-amp. You can now find that G sub C of S is minus the impedance of that feedback set of parameter values, R2 in series with C2, over the impedance created by this parallel combination of R1 and C1. And that's all there is to it to actually create or realize a controller. You can build a controller, go over to the stock room, pull out a breadboard, ask for some parts, and now you've built a controller. Now you may have to worry about the interfacing. Maybe this little controller can't give you the power that you need to drive your system, but this now shapes the signals in the way that you want. It takes the air signal, E, as its input, probably, and then it produces some output signal, which is the U, that drives your system. And here I've simply provided some of the details as to, I think, the solution to one of your homeworks on homework number 1. It's not that challenging now after you've gone this far into the semester, I hope. So now you're seeing that you have a couple of factors, and those factors actually end up, both of them, in the numerator of your transfer function G sub C, and then you have a single S in the denominator. There's also some R1, C2, but you could think of that as scaling the entire transfer function. In essence, this is what you have. You have a gain K, which is really 1 over R1, C2. You have a time constant for one of those zero factors. Where's the zero located? Well, that's at S equal to minus 1 over tau 1. Where's the other one located? Well, that's minus 1 over tau sub 2. So now you have the ability to sprinkle two zeros on your complex plane. The pole is fixed. That's at the origin. But this now represents a PID controller. We've talked about 2 poles and a 0. This is now 2 zeros and a pole. So we have all sorts of different lead-ins to the story that we might want to tell relative to a root locus or a controller. And now if somebody says, well, build me a controller, you can say, okay, I can build you a controller. You want a phase lead? You want a phase lag? You can build it out of op-amps and R's and C's. And here is a combination of those two, a phase lead and a phase lag. Phase lead helps us do what? What's the phase lead help us generically, if you're thinking about it, do for you? Do you remember? What did we say when we wanted to achieve some triangles, some particular dominant closed-loop poles? Oh, our root locus isn't even close to those dominant poles. We need to dramatically change the shape of the root locus. Bing, 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 phase lead, phase lead. What if we wanted to improve the steady-state accuracy? If we want better accuracy, that means if I put in a 4, maybe I want to lock right into that 4 in the steady state. That's my steady-state accuracy. Maybe to do that, I put in a pure integrator. And boom, that's in that PID controller. I have a pole right at the origin, but that's a phase lag behavior. Hopefully now, when somebody says G sub C of S, you have a better feel for what that means. Now you can say, oh, that's an op-amp circuit that I can create and select. You now have 4 parameters, and you essentially have 3 variables that you're selecting, a gain and 2 zero locations. Again, the pole here is fixed at the origin. So let's now today go through that using everybody's friend, everybody's favorite, the mass spring damper system. You know where that's coming from. You can see that. That's under your pillow on one of those 50 index cards that are scattered all over your apartment or house or whatever. But now you pick one up and you can tell a story relative to those index cards. Here is a representative mass spring damper system. It may not be yours, it may not be somebody else's, but maybe it's somebody in this class. It's close. And I think you can immediately see from the way that I factored this denominator where the poles are. The poles are at -2 plus and minus J20. This isn't a real great second order system if you wanted to have small overshoot, is it? But that system in the lab doesn't have a lot of damping. It likes to shake when you push it. You say go to 2000, well, it shakes a little bit in getting there. See, that's why you have to face the instructor. You never know when somebody's going to be shaking. And now, on the exam, you're going to all be shaking, and somebody's going to go, what in the world was going on with your class? Oh, they were trying to understand percent overshoot and omega sub d, sigma. But now, what's the DC gain? Let's move on. What's the DC gain? Can you see that from the way this system transfer function has been parameterized? It's actually screaming at you, isn't it? The DC gain. The DC gain, how do you find the DC gain? If you just had to do it, if you were, I don't understand what he's trying to get me to see. I just know the DC gain. I can find it by setting S equal to 0. So now if we look at this transfer function, when S is equal to 0, what happens? Well, downstairs we have 2 squared plus 20 squared. And I've actually factored that out from the numerator. Those two factors cancel, and I hope you can now see that the DC gain is 12.3. So now you know where the poles are, what the DC gain, so what's the DC gain tell you? If I put in a 1 to this system, where is it going to end up if it's stable? Is the system stable? Yes, our poles are in the left half plane. They have a -2. It may oscillate, it may shake, but it's e to the minus 2t in terms of its damping. And now if I put in a 1, can you tell me where you expect the output to be after all of the shaking? 12.3. That's the DC gain. All right, so now what happens if we don't feed anything back, if we just apply a signal to the input to this system? What's the open loop behavior? For example, what's the 2% settling time for this system? Can you tell me? Well, that's now in this, if we're just wanting the 2% settling time, that's 4 tau. But tau is reciprocally related to sigma, and we now know what sigma is. Sigma is 2, so our settling time, so you only get to see 2 seconds of shaking. So you have to kind of be watching or you will miss that shaking. It only happens for 2 seconds. That's infinity now, isn't it? Infinity is like waiting until the settling time has completed. That's when 2 seconds is the same as infinity. What? You now understand what that means relative to this class. What else can we say about the behavior? What's the percent overshoot? What do we need if we were interested in percent overshoot? Do you see where those poles are in the complex plane behind your virtual reality glasses that you now have on in the screen that you're looking at in your head? They're over -2 and up 20, aren't they? In the complex S-plane. What does that tell you? What kind of an angle? Does that tell you anything about percent overshoot? Well, let's find the angle. The angle theta is now, I go up 20 and over 2. Wow, inverse tangent of 10. That's a pretty big angle. 84.3 degrees. And zeta is just the cosine of that. What's the cosine of 90 degrees? What's the cosine of 0 degrees? Those are the two extremes. So cosine of 0 is 1. Cosine of 0, what did I say? Cosine of 0 is 1. Cosine of 90, too much shaking going on. Cosine of 90 is 0. So we are expecting to be closer to 0. If we compute that, we end up with zeta of 0.1. Then all we have to do is pull out our handy-dandy figure 5.7 and say, I have a damping ratio of 0.1. Woo! What's my percent overshoot? More than 70. So you can quickly then understand, here's now figure 5.7. We have a percent overshoot. Let's just say 73%. And we may not be happy with that. You may not like that much overshoot in getting to your destination. And for that reason, now maybe we want to introduce some controllers. And some controllers then say, let's put it in to our system. Here's our controller. Here's our plant. There's our mass spring damper system. We'll measure the position. We'll feed that back and compare it with our reference and see how that now influences the output. Suppose now we say, let's evolve these controllers. Let's see really how complicated of a controller I need to achieve the behavior that I want. So let's start basic. Let's just say that we want a pure gain controller. That means that we just have G sub C of S equal to K. And do you remember how to make a gain out of an op-amp circuit? If you wanted to make this into a gain, what would you do? How would you modify that circuit? Get rid of those caps, right? Just remove those capacitors and now you have 2 resistors and you have a gain. There's a pure gain controller. So we can build these controllers. You just need a stock room, okay? And we've got a stock room. Okay. Well, this is the last time I get to see you for a week. It has to be a good lecture, right? Or it has to be fun. So, what's going to happen to our system if we apply a pure gain controller? We're at -2, and now the scales may not be very equal, but we now have two poles right there in our complex S-plane. What's going to happen if we introduce a pure gain controller into this pole zero diagram? I'm asking for what? We now have become sketch artists, right? What are we great at sketching? Or you better be by a week, in a week. You can now sketch red lines or root locus diagrams. What's the root locus of this look like if I introduce just a gain for my controller? And you're going, well, let me see. First rule, plot the x's. Done. Second rule, what real line segment or segments belong on the root locus? The whole thing? Is that part of the root locus? How many poles and zeros are to my right on the real axis, anywhere on that real axis? I don't have any, and 0 is even, right? It's not odd, so I'm not going to be anywhere on that real line. Okay, now I have two poles, no zeros. What's my pole zero excess? 2. What's that tell me? Divide that into 180. We have 180 divided by 2, that's 90. So our fundamental angle is 90. And 270 or minus 90. So now we're going straight up. Where's sigma sub a? Where do we pin those asymptotes? Where do we pin those angles? Sigma sub a is the real parts of the poles minus the real parts of the zeros divided by p minus z, the pole zero excess. Minus 2 divided by 2. Sigma sub a is at minus 2. Does that tell us what the root locus looks like? I didn't give myself enough room, did I? If I put this into a closed loop configuration with just a pure gain controller, am I going to enhance my settling time? Or improve it? We've got to have a cheer. I forgot which one it is, but what's the closed loop control transfer function for this system? What's T sub C if I have a pure gain controller? Really? Just because it's a bye week doesn't mean you have to forget your cheers. kg over 1 plus kg, right? So here we have kg over 1 plus kg, and we've now sketched what 1 plus kg looks like as we adjust k from 0 to infinity. We just go up in vertical direction or down. What's the settling time? Does it vary as I adjust k? No, I'm stuck right at minus 2 for sigma, so my settling time is 2. What's the percent overshoot? Does that depend on k? Whole lot of shaking going on if we crank up the k, right? If we make k bigger, what's going to happen? That angle theta is going to get closer and closer to 90 degrees, and zeta is going to get closer and closer to 0. And we know what happens in that situation based on figure 5.1. So let's look at what we can maybe do here. Here's T sub C. For our particular case, this will end up being something like, there's the numerator. Whoops. That's supposed to be a k. It looked kind of like a 4 to me, but this is now s plus 2 plus 20 squared plus k times 4969. That's now the closed loop transfer function. What if, we know it's not going to do very well if we crank up the gain a lot k. let's just look at a small k so that we're just inching a little bit vertical relative to where we started, which was minus 2 plus and minus j20. Suppose we let k equal 0.1. Now I can do the math, right? The denominator is now s plus 2 squared plus 20 squared plus 496.9. Or, if I now combine those constants, I know that that piece hasn't changed based on my understanding of the root locus, but now I can find some value which when squared would give me 400 plus 496.9, or 20 squared plus 496.9. Basically 900, right? What's the square root of 900? 30. So I'm close to 30 with a gain of k equal to 0. And this is actually, boy, I'm really getting precise today, 29.95. What's that angle? Can you now tell me what my percent overshoot will be for a k of 0.1? Now you can find the angle, and that would be the inverse tangent of 30 over 2, or the inverse tangent of 30, or I probably plugged in all this accuracy. We take the cosine of that angle and we get zeta, and we know it's going to be small. Zeta is now equal to 0.067. Or that now, based on figure 5.7, you know how to do that. Whew! We're way up there above 80 when we're under 0.1, 0.07 for a zeta value. So now our percent overshoot is 81%. And maybe that won't cut it. Maybe your boss says, no thank you. Okay, you learn control, you know how to close the loop, you know how to build a controller, you build a gain controller, get a little bit more creative. Make that a little faster in terms of make the settling time, reduce the settling time, shorten the settling time. And what's going to happen if we reduce the settling time? Where do we need to push those branches of the root locus? Further into the left half plane. So we need to, let's say we want to speed up the response. That means that we want to drastically change the root locus shape, and that means what kind of a controller, if we want to start just one nudge up from a pure gain. Now maybe we want a first order controller, we maybe want just one pole, then maybe a 0. What kind of phase do we want? Lead or lag? Phase lead is what we want. So now let's look at what we might be able to accomplish with a phase lead. Now, in physics, did you do a bunch of thought experiments? Did you just try to think about what might happen? Oh, I mentioned the bad word physics, didn't I? Sorry, now I've lost everybody. Now no one wants to listen anymore. I've already said physics. Okay, forget that. Back up, rewind, and skip ahead. Rewind and skip ahead. That didn't make any sense, did it? No. So just skip ahead. Here we go. Speed up the response. Here's a thought experiment. You don't do this. Don't do this at home, but let's just think about it. So I'm going to try to, in case you're just looking at the notes and not listening to these great videos, at least you have what I tried to say, thought experiment. So here's a thought experiment. We have two poles here, and we want to pull them over into the left half plane. What if we put a 0 right there? Just a pure 0. That's what we don't want to do. We don't want to just add a pure 0 because that's a differentiator. And what would happen if we had kind of a noisy signal in the air and we differentiate it? If we have something that's shaking and you differentiate that shaking, what happens to the shaking? It makes it more, doesn't it? You differentiate shaking and it gets worse. So we don't really want to have a pure zero in our system, but here we're just trying to think. This is a thought experiment. What's the root locus look like for this configuration of poles and zeros? 2 poles and a zero. Walk into it. Remember? This is now 2 poles to the right of a zero. You can pull out your compass and draw this. There's the radius, and the center is the zero. We can now, I won't be able to draw it, but you can use your imagination. That's what would happen. Does that move our root locus or change our root locus shape dramatically? Yeah. Before we were just going up and down. Now we've moved over. We have moved our... So this is, what do I want to say? This is the process of adding only a zero. Again, I'm filling in for those of unfortunate individuals that don't listen to this. They're just reading the notes. Adding only a zero, not realistic. And what did I say that is? A pure zero. What kind of action? Now I'm going to mention another bad word, calculus. Boy, we're using all of these bad words today. Physics and calculus. What did I say was associated with a zero that you can connect with calculus? Differentiator. So now you can build a differentiator with some electronics, but we would want to actually roll off that derivative action. We would want to put a pole far enough into the left half plane to roll that off so that we just don't keep differentiating at high and high frequencies. But this did, I hope, it helps our insight. That's the whole point of this thought experiment. Okay, if we can't do this, what can we do? Well, you said we could add a phase lead. So what's a phase lead controller? If we exaggerate a little bit the difference between that zero at minus z sub c and that pole at minus p sub c, do you see that maybe we are pulling the root locus over with that zero? And if we really stretched the distance between z sub c and p sub c, maybe we could almost neglect p sub c, and now we're back to that differentiator. Pure differentiator. Here we have a modified differentiator, but what's the root locus of this look like? This is now g sub c of s equaling k s plus z sub c over s plus p sub c. What's the root locus of that look like? Do I have any segments of the real line on my root locus diagram? That pole's going to go over there. And depending on how far apart those poles and zeros are, you could have several different scenarios. If you really push the pole out, you might be able to do this and then things would break away. We're not going to push that pole that far. What's my asymptotic behavior look like? What's the asymptotic behavior based on? The asymptotes, but what governs those asymptote angles? the pole zero excess. We have 3 poles and a 0. Our pole zero excess is still 2 like it was in the original system. So we are eventually going to approach asymptotes at plus and minus 90. Which means that we now might be doing something like this, where those asymptotes sigma sub A is going to be influenced by the poles and zeros locations, and those are now where we will approach with our closed loop poles using a phase lead controller. And we might now want to locate our closed loop poles here and here. How many closed loop poles do I have? How many poles were in my original system? 2. Have I added any poles? Yes, that phase lead controller added one. So I now have 3 closed loop poles. Where's my third pole? It's somewhere between that minus P sub C and minus C sub C. Right there, let's say. Now we have 3 poles influencing the behavior. And what I would suggest is now I've actually given you a script. It's not what you would read on stage, it's what you actually give MATLAB, and MATLAB reads that script and it performs. And it's a phase lead controller design script, so I would say see MATLAB and the Lab 2 material for the design details. But I hope that you now have a little bit of a feel for what you could do with a phase lead controller. You can modify the root locus. And I think in lab number 3, I've called that script phase lead.m. And that's in D2L. You should be able to find that, and that will allow you to manipulate the poles and the pole and zero of your controller to see how you can now move those triangles around to achieve the specification that's requested in one of the parts of lab number 3. What if somebody said, okay, I want to create a PI controller. G sub C, well, PI actually gives you a hint. That tells you what the controller looks like. It's a proportional piece and it's an integral piece. There's a PI controller. We're just adding up those 2 types of control actions. The proportional works with the present error. The integral works with previous errors to try to eliminate the error in your system. If we now said, well, I can't see what that's doing, that's a parallel combination of proportional and integral on your error signal. But if we put that over a common denominator, this is looking kind of familiar. So now let's factor out K sub P. And now we have a controller 0 that we can manipulate around. We can move by the adjustment of K sub I and K sub P through that ratio. And we can adjust the gain through K sub P. We're stuck with a pole at the origin, but that pole at the origin changes our system type. And our system type influences steady state accuracy. So this can help us improve steady state accuracy. And you're going, take off the training wheels. I want to just ride this bike. Well, okay, let's go PID. Let's add one more piece to this controller. A PID controller just a heads up if you're interviewing and somebody says, oh, tell me about this PID on your resume. Then you'll have to gracefully explain, oh, the PID controller, we don't call it a PID, do we? No, it's a PID controller. So this is a combination of phase lead and phase lag, or you now can write down on the piece of paper in front of you for the interviewer's enjoyment what the PID controller is. It's P, K sub P, plus I, K sub I over S, and now we have derivative action, K sub D S. We know we really probably don't want a pure derivative, but we're going to assume that in the ideal case for this class. But in practice, this would probably be over some fast pull factor so that it rolls off that derivative action at high frequencies. We'll just kind of wink and nod and say, we're not going to worry about that. Let's just design with P, I, and D without that blue term underneath. So now if that's the case, we can actually put all of this together, getting a common denominator, and now we have K sub D S squared plus, you can do this tonight on your own. I know that you're going to want to do that. Put all of this over a common denominator, and there is now our PID controller. That's just a quadratic expression in the numerator, which we know can probably be factored and Z1 and Z2 could be real and unequal. They could be real and equal. They could be complex conjugate of each other because we have a quadratic expression. There's our PID controller. If somebody now says for the exam on Friday, oh, use a PID controller, you can jump to this particular expression. I don't need to see the K sub P term, the K sub I term, and the K sub D term. I just want you to sprinkle 2 zeros and a gain and tell me what happens to the root locus. Or use that to adjust or achieve certain triangles in the closed loop configuration. What are some possibilities? Now we can just start playing. Suppose now we have this S-plane. We're starting again with the same given plant, the mass spring damper system, -2 plus and minus J20. What's this PID controller tell us? Well, it's forcing a pole at the origin. What's that pole at the origin do? Why would we put a pole at the origin? What's that do? Okay, I'm going to have to remind us of that bad word. Calculus. What operation are we doing now? A 0 corresponded to differentiation. Now that pole is a pure integrator. That pole at the origin is a pure integrator. That's integral action. It integrates the air. But we have more than that in this PID controller. We have a pole at the origin. That's fixed. We don't have to design that. That's already fixed. That gives us what? Better steady state accuracy. But now we are actually, with this ideal scenario, I said we're neglecting this piece, didn't I? Neglecting that red factor, now we've changed our pole 0 excess. We have 2 zeros and a pole. Oh boy, that's going to help us. And this is the ideal design scenario. Now we get to place 2 zeros. Suppose somebody says, oh, I want to put 2 complex conjugate zeros right there. Because what? Those zeros are going to try to pull those poles towards them. So what's the root locus look like for this? Pole 0 pattern. do I have any real line segments on my root locus? How many pieces of French bread do I have? Why did I mention that? Now I'm hungry. And I have a late lunch today. How many pieces of French bread do we have? Nobody else is going to understand a word of what we're talking about now, but you guys, I hope, do. We have two sections of French bread, a positive and a negative. Which one belongs to the root locus? That's on the root locus. How many branches of the root locus do we have? 3. Where are those other 2 branches? What's our asymptotic behavior? What's our pole zero excess? Quit asking so many questions. It's kind of the same question, isn't it? We have 3 poles and 2 zeros. Our pole zero excess is 1. We divide that into 180. Our asymptotic action is just happening at minus infinity. So the other 2 branches terminate on finite zeros, and that's what our root locus would look like. And now we could crank up the gain to maybe put us there, and we have 1/3 pole, and if it doesn't sneak very far, which one would we agree to use or which of these would we agree to use for our settling time computation? The one closest to the origin. So now maybe we haven't sped up our system as fast. Yes? Where did the 90-degree asymptote go? Here, boy. Where did it go? Can we find the 90-degree asymptotes? We're kind of cheating, aren't we? We're cheating because we started with a pole zero excess of 2, and now we have a pole zero excess of 1. Why? Because we've agreed to forget that red S plus P sub F factor. So now we have 2 zeros and 1 pole being introduced by our controller. So we have how many poles? 3. How many zeros? 2. So now our pole zero excess is 1. Those asymptotes 90 and plus and minus 90 have vanished. We've performed some magic, haven't we, by this? And we've agreed that magic is really coming because we're neglecting that S plus P sub F factor. So now we don't have asymptotes at plus and minus 90. That's one possible pattern. What's another one? Well, we have all sorts of possibilities because we have the ability to put down 2 zeros. In the previous diagram, we picked 2 complex conjugate zeros. What if somebody says, oh, I'm going to make 2 real zeros? Now what's the root locus look like? We've cut our bread into more pieces, haven't we? We've now introduced 2 more cuts on the real axis. We have 1 piece of our root locus there. We have another piece there. This pole at the origin is going to go towards minus z sub 1. And what happens to the poles? Again, we have changed the pole zero excess with this PID controller. That's why it's so powerful in this class. We've now eliminated one of those poles effectively. Where do these 2 complex conjugate poles, where do they go? One has to go off to minus infinity, doesn't it? And the other one has to approach the finite zero, so they're doing this. And I kind of exaggerated that. That's really not a circle. Why? It's kind of nice shape. That's a terrible shape. You can draw yours better. You can plug it into MATLAB and make it nice and clean. But the reason it's not a pure circle is because I have that pole 0 there by the origin. But now what happens if I now crank up the gain K? I can maybe put a... But now I'm stuck there, am I not? That's going to bang up against minus C1, that third pole. Does everyone know how to find the gain K? Man, I can't believe I was having so much time. But this, having so much fun, I was running out of time. I've written a script that's PID1.m. MATLAB has its own PID script, so I had to be creative and rename this one. So it's PID1. But to calculate the gain, you could find all of these distances. And divide and multiply by the appropriate lengths of the zeros and the lengths of the poles and the gain constant to get the gain K associated with this. And I may add on after class some notes to sort of be a little bit cleaner on how we would find the gain for our PID controller. Good luck on your exam. That's in a week. You don't need to show up for this class until then, but please show up for the exam.